Everybody see the cartoon? Okay. So we have to put all this in context. Today, the buzzword in medicine is personalized medicine. For example, we know that men and women react very differently to certain drugs and certain diseases, cardiovascular disease and myocardial infarction being top of the list. We also know that there are ethnic differences. This is a report from the New England Journal of Medicine in 2006. And it says, among cigarette smokers, African Americans and Native Hawaiians are more susceptible to lung cancer than whites, Japanese Americans, and Latinos. Same number of packs smoked, et cetera, et cetera. Ethnic differences. And today we also know that there is a large body of literature showing that identical twins do not always get the same disease and do not always react the same way to drugs. Okay. If a man cannot be used to predict what a drug is going to do in a woman, if there are differences between races, if there are differences even between identical twins, what do you think the probability is that an entirely different species is going to be able to predict what smoking does to a human or what a drug does to a human, and so on and so on? So, we usually hear four things from the animal model community. We hear that we must use animals to predict human response. And the old adage is very familiar. Would you take a drug that had not been tested on an animal? Well, yes, I would. I would also take a drug that had not been tested on my car engine because it's a non sequitur, okay? Regardless of what the drug does in 15 different animals, we still don't have any idea what it's going to do in humans. Okay? Then you'll hear the animal model community say, well, we must use animals to study human disease. We want to see how HIV infects the white blood cell, and so on and so on. But a lot of studies of animals, for example, smoking, heart disease, environmental poisons, and so forth, again, prove that animal models are actually misleading, and they're certainly not predictive. So the question then becomes, should we use animals in basic science? This is not a basic science debate tonight. This is a debate about predictability. But maybe we should use animals in basic science. Now, before we make that decision, there are some very legitimate questions that we can ask. What has been the track record when using animals? What has been the track record when not using animals? Is there a difference between using vertebrates and invertebrates, and so on and so on and so on? Again, that's a debate for another time and another place. And finally, you'll hear people say, well, we don't have any other options. Well, yeah, we do. That's like saying, what will we do if we don't eat apples? Well, we'll eat the other 99% of food. I mean, there are myriad options that are scientifically viable. So, in closing, I would challenge Eric tonight to provide published, unbiased studies, not anecdotes, proving that animal models per se are predictive. Not that they're useful, not that the FDA requires them, not that they're heuristic, that they are predictive. And there must be enough studies to offset the ones that I have already presented. And remember, it takes far less to prove a hypothesis wrong than it does to prove a hypothesis right. And he would need to explain why the studies that I quoted are actually the exception. He would also need to explain why the theory of evolution, complexity theory, evo-devo, gene regulation and expression explain species differences while simultaneously allowing for one species to predict the response for another. That's almost a contradiction. And finally, he would need to explain why many in the pharmaceutical industry, the FDA, and the NIH agree without discussion that animal testing is not predictive for human drug response. And again, thank you very much.
Okay. Thank you, Dr. Greek. Just as a reminder, if you do have any questions at this point, just jot them down on those pieces of paper you have and pass them to the center aisle, and Susan will collect them. Now, next we have Dr. Sandgren in his response to Dr. Greek. He has 35 minutes.
So I would like to start out with some of the same thank yous. I very much appreciate the Capital Times and Dave Zwiefel for sponsoring and hosting this. It's an important issue, not just to all of us here, but to a lot of other people. I would like to thank Rick Bogle and his colleagues for initiating this. And I also would like to thank Dr. Greek for two things. One, for attending, and two, for so nicely outlining for me in his final slide what it is I'm supposed to talk about tonight. And I'm sure I would have done that if he'd let me know a little bit earlier. But instead, I'm going to take a slightly different approach. And there are two ways of addressing issues. Actually, there are many ways of addressing issues, but I want to contrast two of them. This contrast is, I think, illustrated very nicely by something called Zeno's paradox. And there are a number of ways to put it. The one that I think is the most straightforward and the quickest to tell is that when you are approaching a subject from the outside, when you really don't know how it works, but rather you're just looking at it, reading about it, perhaps applying logic to it, you can sometimes trap yourself. So Zeno's paradox is this. The conclusion is it's impossible to walk from one side of the room to another. And the reason for that is, first you have to walk halfway, and then you walk half of the remaining distance, then half of the remaining distance, then half of the remaining distance. And you will never be able to go all the way because those halves are infinite. Don't worry, I'm not going to actually walk across the room. I don't need to do that. I just tend to wander, and I know I will trip if that's there. And to a certain extent, the presentation I've heard tonight reminds me of that. It's a look from the outside, not a look from those who actually do animal research and understand how the data is used. So there's a very simple way of solving that paradox. And the story is that when this was brought up among some ancient Greek philosophers, one of them finally got disgusted and stood up and walked across the room. And in a sense, that's what biomedical scientists do. So I'm going to actually have a slightly different presentation. What I want to do is really formulate this as a story. And from my perspective, this is a non-fiction story. I'm sure Ray will not agree with that. So that's me, and what story I want to tell is how scientists precisely match the questions they ask to the tools, and sometimes those tools are animal models, that will give appropriate answers that in some cases will be predictive. And there are some ways in which I agree with Ray on his definition of predictive, but there are others in which I do not. I do not think an animal model has to be identical to a human, or the same 19 times out of 20, or the same 9 times out of 10, in order to be predictive. An animal model may be very different from humans, but in one aspect of its biology, it can be predictive for humans. So I'm going to tell some stories about how scientists have used animal models to be predictive, and do this from a historical perspective, starting in an area where Ray would agree that the use of animals was appropriate, and then carrying it up to some studies that have been done today, and along the way making a few other observations. So I'd like to talk a little bit about some of the things that I've learned from Dr. Greek over the last few days, in person and, examining his website, which is listed up there. And notice I'm giving you the free publicity there. I think it's definitely worth looking at that. So he commented on this earlier, that there are a number of acceptable ways to use animals in medical research. And by and large, I would agree with that. He also commented that there are several scientifically unacceptable ways to use animals. Animals as models for disease. Animals as test subjects, for example, drug testing. And that's really where we get into the issue of prediction. How well and how do or do not the animals predict what can happen in humans? Here are some other comments that I've taken from the presentations that he has on his website. And again, I think these he's reinforced tonight. the animal model must be predictive to be useful. And I would agree with that, although I don't necessarily hold the same definition or apply the same definition that he applies. And basically, the animal model has outlived its usefulness. It was useful in the past, but now we have gone beyond in our knowledge the stage where we can use information from animals. The differences between species outweigh their similarities, in other words. And that was one of the issues he got to in his last slide. Certainly, evolution has created animals that are separate from each other. He also claims there is not an alternative to animal models to study human disease. And I hope he does come back to that a little bit later on, perhaps in his rejoinder, because I'm not quite clear on what he means. But he says because animal models are a non-viable way to study human disease, there's no alternative to them. That's not the way I use alternative. But he then even further states we cannot consistently rely on members of our own species as being models or as being predictive. And again, he mentioned that as well. He talked about how identical twins, in fact, could be very different. We'll come back to these, but those issues pose some problems in terms of how science can be conducted. And finally, Eric Sandgren says, animals and humans are not identical. And I think that's something that everybody recognizes. And that includes scientists. Animals and humans do have much in common, though. Also something that everyone recognizes. Animal models have in the past been predictive. And I think up to this point, Ray and I perhaps agree. But we break at the point where I say animal models continue to be predictive. I'm going to show you an example. An example may be counted as an anecdote by Dr. Greek. But examples give you a sense for how science is actually performed. And again, that's the story that I'm trying to tell you. How it is that a scientist uses animals in such a way, given the differences and given the similarities, so that they can be predictive. And I also think the ideal approach to the study of human disease generally is to combine animal and human studies. So there is clearly a place for studies involving humans in the understanding of human disease. Whether or not identical twins are different, I still think it's important to use humans in that study. So remember, as Ray said, we are talking about prediction here. We're talking about predictability. We're not talking about a number of other uses of animals. We're really not talking about ethics either. Although ethics, I think, is as important an issue as efficacy when we're talking about using animals or using humans for that matter in research. All right, so my outline: history, current events, and the future. Can there possibly be a more generic outline? But I wanted to just let you know what I'll be talking about. This actually came with the PowerPoint program. William Harvey and the circulation of blood. This is an example that he brings up in his website and talked about earlier, and I want to reiterate that and show how it gave an example where perhaps we both agree that animal studies can be predictive. So earlier Galenic views, centuries old, were that venous blood originated in the liver and provided nourishment and growth. Arterial blood originated in the heart and provided vitality. I'm not sure what vitality means in this context, but it sounds good. And that each type of blood flowed then from those organs to all parts of the body. And this is something that had been believed for thousands of years. Harvey discovered, based on controlled studies using a number of different species, and he spoke about this in 1616 and published in 1628, he determined that blood was pumped around the body by the heart in two closed loops, the pulmonary loop and the systemic loop. And now, today, we consider this obvious, but of course, after the fact, after something's been discovered, we always consider something obvious. Things that were only discovered a year ago to the scientist actually now are obvious. Scientists move forward, basing their work on what has come before. And that was really the dramatic part of this. It was a tremendous step forward relative to what had been known before. He was followed by Marcello Malpighi, who was considered the first microscopic anatomist. That doesn't mean he was tiny, it means he used the microscope. And he identified the capillaries, which were the connections between the venous and arterial systems that Harvey had not been able to identify, but could only speculate about using frog skin, another animal model. So for understanding of organ structure, physiology, and function, animals have been predictive. This is one example, and this is something that Ray also stated, that for understanding these basic processes, animals can be predictive.